Organic chemists often use bond line drawings to draw molecules. Consider, for example, the following compound. The carbon atoms and hydrogen atoms are not explicitly drawn, but they are implied by the drawing. In these drawings, the sticks represent the electrons. For example, this bond here represents the two electrons that form the bond between these two carbon atoms. These two electrons occupy an orbital that we call a molecular orbital. A molecular orbital can be thought of as an electron density cloud centered between the two carbon atoms. These drawings are very useful, but they suffer from one major shortcoming. There are many circumstances when electrons are not located directly between two atoms, but rather they are spread out over a larger region of the molecule. For example, consider the following vinylic carbocation. In order to capture the essence of this carbocation, we must actually draw the following two drawings, and we must meld these two images into one picture in our minds. Neither of these drawings adequately captures the essence of the carbocation. The electrons are not here, and they are not here. Rather, they are spread out over this region of the molecule like a cloud. Care must be taken here. The curved arrow might suggest that something is happening here, but that is not the case. The carbocation is not doing anything. It is not vibrating, nor is it resonating the way a tuning fork resonates. To understand what we mean, let's use a simple analogy. Imagine that you have a friend who has never seen a nectarine before, and he asks you to explain to him what a nectarine is. You would probably describe it like this. A nectarine is a hybrid fruit that you get when you cross a peach and a plum. A nectarine is not a peach, and it is not a plum. It is certainly a unique fruit, but it has qualities of a peach and qualities of a plum. The nectar and the pit are similar to a peach, but the peel has no fuzz. It is smooth like a plum. The color of the peel is somewhere in between the color of a peach and the color of a plum, although many nectarines will often look very much like peaches. Now comes the important part of the analogy. Imagine that you videotape a nectarine. If you were to watch the videotape in slow motion, frame by frame, do you think that you would find that a nectarine is really just a fruit that is vibrating back and forth between being a peach and being a plum? Of course not. That is ridiculous. A nectarine is a nectarine all of the time. It is not vibrating, it is not resonating, and it is not doing anything. The only reason we described it in terms of a peach and a plum is because your friend had never before seen a nectarine. So we described the qualities of each fruit so that your friend could picture in his mind what a nectarine is. This is exactly how we deal with the inadequacy of our molecular drawings. The carbocation shown here is not vibrating back and forth between two different states of existence. The carbocation is one entity, all of the time. But unfortunately, there is no one drawing that can capture the nature of its essence, because any one drawing would be inadequate. The way we deal with this inadequacy is to draw two drawings and meld them together in our minds, just like the peach and the plum. We call these two drawings resonance structures, and we draw a two-way arrow and place brackets around the two drawings to indicate that they are resonance structures. In other words, the term resonance does not actually describe anything that the carbocation is doing. The carbocation is not doing anything. Rather, the term resonance is the term used to describe how we deal with the inadequacy of our drawing capabilities. The curved arrows are misleading because they cause us to think that something is happening, that electrons are moving. But these curved arrows do not describe the motion of electrons. Rather, these curved arrows are tools that you can use to help you draw out the resonance structures of a compound.